Okay, chapter 1.4, collecting data to understand causality. Often the most important questions in science, business, medicine, etc. are questions about causality. For instance, does smoking cause cancer? Will eating an apple a day keep the doctor away? Will taking this medicine make me feel better? Does studying a foreign language improve a person's verbal skills? If someone claims that the answer to any of these questions is yes, then how do we know whether to believe their claim? All right, so number 2, we're going to look at a bunch of questions, the types of research questions. So notice that the 2 variables are given in each of the following questions, and we're going to identify the 2 variables. So just a reminder to be careful. We want to make sure that we phrase these variables. We're going to be careful with our phrasing. Okay. We want to make sure that the variables are specific to each observational unit. So we want to be careful with our phrasing so that it indicates that. So this means that the question is one that an observational unit, a person, can answer. They're going to be people in this case. All right, so for instance, does smoking cause cancer? Here are 2 variables. We're going to be interested in whether the person smokes and whether or not they develop cancer. So do you smoke? Okay, that's something that your observational unit, the person, can answer. Did you develop cancer? This is done down the road. It could be, do you have cancer? Did you have cancer? So there's going to be a couple different ways you can phrase each of these. All right, and the second one, will eating an apple a day keep the doctor away? So we're interested in something about apples and something about doctors. So one variable would be to ask the person, do you eat an apple? Oops, I missed the word eat. Do you eat an apple a day or every day? Okay. Second one, there's a couple different ways you could phrase this. How many times have you visited the doctor? Might be one. Notice this is phrased in a numerical way. You're going to be counting how many times they visited the doctor. You can also say, have you visited the doctor? Make it more of a yes-no type question. But either way, they're specific to each observational unit. All right, next one. For instance, will taking this medicine make you feel better? All right, so if we're asking the person, we might ask them, did you take this medicine or the medicine? Assuming they understand or have access to the type of medicine we're interested in. And then the other question might be, how do you feel? Could be, do you feel better? Again, a lot of different ways to phrase that, but we want to make sure it's something that is specific to the observational unit. So do you feel better would be yes, no. How do you feel? You might give them choices like better or worse or same. Next one, does studying a foreign language improve a person's verbal skills? All right, so one question asked the observational unit, did you study a foreign language? And I'm going to abbreviate that with FL for foreign language. And then, did your verbal skills improve? That would be a yes-no type question. We could also ask, what's your verbal score? What's your verbal test score? And that would be numerical. But both of these are specific to the observational unit, meaning that each observational unit can provide an answer to that. All right, and the last one, will doing your homework help improve your grade? All right, so one question to ask the observational unit, did you do your homework? We might ask them what their homework grade is. We might ask them how many homeworks did they do, or how much of their homework did they do? So again, a couple different ways to phrase that. And then improve your grade. We could ask, did it improve your grade? Make it yes, no. We could ask them, what is your grade? And that may be numerical if you're looking for a number grade. Be categorical if you're limiting them to letter grades. Okay. So below that, most questions about causality can be understood in terms of two variables. We're going to have the treatment variable, which can also be referred to as the explanatory variable. And we have the outcome variable, which is also referred to as a response variable. These questions are essentially asking whether the treatment variable causes changes in the outcome variable. So identify which variable is the treatment variable and which variable is the outcome variable in the questions above. And just as an aside, this idea of causes, think about if you're walking across your kitchen and you stub your toe. Stubbing your toe is the action and it causes pain. So think about, again, the cause and effect. What happens first in some sense, in some cases? Right, so if we go back up to this example, does smoking cause cancer? They use that word. It helps us clarify which is which. So smoking is a treatment variable. We're going to abbreviate that with T. And then we're looking for this outcome. Do you end up getting cancer? Right, so that's the result of the smoking. And does smoking cause cancer? All right, second one, will eating an apple a day keep the doctor away? So don't use the word cause, but they're interested in whether the apples have some effect on whether or not you're healthy. So eating the apples, in a sense, comes first. That's your treatment. And then how many times have you visited the doctor? That's as a result. Is it affected by eating the apples, caused by eating the apples? That's our outcome. All right, number 3, will taking this medicine make me feel better? Medicine is more commonly thought of as treatments. That was a little easier in that sense, but it's still like the previous two in that it's coming first. And we want to know whether or not that has an effect on your health. So whichever way you phrase it, these two things are your outcome variables. All right, number 4, or D, does studying a foreign language improve a person's verbal skills? So the foreign language is your treatment variable because we're interested in whether or not that affects your verbal scores. So this is the end result, the outcome variable. All right, and did you do your homework? That's your treatment variable. And we want to know how that impacts your grade. So your grade is the outcome variable. Okay, so number 3, let's consider one of the questions from above. Will eating an apple a day keep the doctor away? So let's say if you recall that one of your high school friends ate an apple every day and never went to the doctor and was never sick. Could you conclude that eating apples caused this person's good health? So we're looking for that causal relationship. You want to press pause and give this some thought. Most of you are probably thinking no, and hopefully what you've thought about is that there's too many other things to consider. Okay. It's also just one person, so it may be an anomaly or a fluke. There's a lot of variation and diversity in people. Be a lot of other things that one particular person is doing. So this is an example of what we call an anecdote. An anecdote is essentially a story that someone tells about his or her own experience or the experience of someone they know. Anecdotes are not very useful when it comes to answering the question of causality. But it may be useful in the sense that it gives you an idea to research. So you can't prove causality, you can't suggest causality from it, but it may give you something to research that you're interested in. Right, number 4, what if a study takes a look at a group of people and asks them whether or not they eat apples regularly and whether or not they visited the doctor in the last year? The people that eat apples are generally healthier than the people that don't eat apples. Can we conclude that eating apples causes better health? So again, press pause, give yourself a chance to think about this. Right? Hopefully a lot of you are thinking, well, this is definitely better than above because there's more people. So again, we're comparing this to the anecdote above. It helps us rule out the fluke explanation from above or the anomaly. It's not just one person anymore. Can't say it's just an exception to a rule. But you're hopefully also seeing that it's not perfect. There's still some flaws here. Right? People who eat apples may differ from people who don't eat apples. They may have better diets, exercise more, socioeconomic status might be different. They might have healthier lifestyles. And all of those things that you thought about are listed. They might contribute or account for the increase in their health or having better health. Right, so some notes about this situation. This study from number 4 includes a comparison group. People who eat apples are being compared to people that don't eat apples. So that's where it gets a little bit better than the antidote. People that eat apples are in the treatment group since they're receiving the treatment of interest, which is the eating the apples. And the people who don't eat apples are in the comparison group since they didn't receive the treatment or the apples. Comparison group note is also referred to as a control group. This is an example. The study is referred to as an observational study. Subjects in observational studies are put into either the treatment group or the comparison group, either by their own actions or by the decisions of someone else who's not involved in the study. So as an example of what that might mean, let's say you've got some children in this observational study, and it's their parents that are doing the grocery shopping. So their parents are giving them their food. They're kind of making those decisions for them, but it's not the researchers. So it's still an observational study in that sense. And note with this kind of that root word, the researchers are really observing. They're not manipulating the subjects in any way. All right, third bullet, since there may be potential confounding variables or potential differences between the treatment group, which is the group eating the apples, and the comparison group, which is the group that didn't eat apples, that may explain why the treatment group was generally healthier. You can't conclude that eating apples causes better health. And the main thing here is these confounding variables give you other explanations for those differences in their health. Okay. And lastly, a drawback to observational studies is that you can never know whether a confounding variable exists, which unfortunately means that you can never conclude a cause and effect relationship between the treatment variable and the outcome variable. This means that we cannot conclude that eating apples causes better health. We can, though, say that there's an association between eating apples and better health. All right, so on an aside, I just want to make a note about a confounding variable. So a confounding variable has to have two features. Okay. In fact, I'm going to press pause and write a note, and then I'll press. Okay, so a confounding variable has two features. So one, it's going to have to affect the outcome variable, and two, it has to affect the treatment variable. So if you're asked to describe a potential confounding variable, you've got to make sure you've got those two pieces in there. So as an example, let's say that you had mentioned that exercise is one of those potential confounding variables up above. You don't want to just stop there. You want to go a little bit further and say that the people that are more likely to eat the apples are also more likely to exercise. So it's the difference between your two treatment and comparison groups. And then people who exercise are more likely to be healthy. So you're offering an alternative explanation for why the one group is healthier than the other. All right, number 5, consider a study that takes a random sample of people and then randomly assigns half to eat an apple every day and the other half not to. The researcher then follows them for a year to see who requires a visit to the doctor. How might this be better than the observational study? So note it is better. You've still got those two groups that you're comparing. There's still that comparison, but this comparison uses something called random assignment. So notice the researchers are imposing the treatment on one of the groups. They're deciding who eats the apples. And hopefully this means the only difference between the two groups is whether they eat the apples. So hopefully by using something called random assignment, which you're going to look at in your first lab, we're going to talk about a little bit below, hopefully what that's going to accomplish is that your two groups get balanced out in terms of who exercises and who doesn't. You got an equal number of exercisers in each group. Socioeconomic status gets balanced out. Their diets, good diets, bad diets, those get balanced out between the two groups. Again, the only true difference is whether or not they're eating the apples. So when this type of study is done, we refer to it as a controlled experiment. In a controlled experiment, researchers take control by assigning subjects to the two groups. This assignment is done correctly. It ensures that the two groups can be nearly identical in every way except whether or not they receive the treatment. In this case, again, the treatment is the apples. And your two groups again are the treatment group and the comparison or control group. Okay. All right, a good controlled experiment uses random assignment to assign participants to the two groups. This can be done with repeated coin tosses, a random number table, or technology. The most important thing is that no human determines the group assignments. We're going to see in Chapter 5 that humans aren't very good at doing things randomly. All right, so the goal of random assignment is to balance the groups so that the variation in diets, weights, heights, ages, etc. are going to be similar in most groups. This will help you minimize bias. Bias indicates that the results of the study are influenced in one particular direction. For instance, if the researcher puts all of the exercises in the group that eats apples, then you've got some bias. All right, if we can make sure that the two groups, the treatment group and the comparison group, are identical in every way other than the treatment variable, then we can conclude cause and effect relationship exists between the two variables. And comparison or control. All right, number 6. Note that random assignment is different from random sampling, and a study may use both random assignment and random sampling, or use just one or use neither. Random sampling refers to how the subjects are selected for the study. In other words, who's going into your sample. And random assignment refers to how the subjects are assigned to each of the two or more groups. Okay, so remember that random assignment from what we saw above, this is what allows cause and effect conclusions to be made. It eliminates those potential confounding variables. Random sampling, on the other hand, if that's used, then the results of the study may be extended or generalized to the population that the sample was selected from. In studies where random sampling cannot be used, which often happens with medical studies, researchers often try to replicate their findings with additional studies and diverse groups of people. So random sampling, again, is going to help you ensure, or helps to ensure, your sample or the sample is representative of the population. And that is what allows you to generalize to the population. If your sample looks like the population and you observe something in the sample, well, then it's safe to say or safe to generalize it or extend it to the people in the population itself. All right, and last one, let's see if I can move this down, number 7. Cause and effect conclusions are only possible with controlled experiments, then why do researchers still use observational studies? Well, hint, think about a study that looks at whether or not smoking causes lung cancer. Right? Check, or in this case, remember that you can't always do an experiment. In this case, you can't randomly assign someone to smoke and someone not to smoke, and that's for ethical concerns or reasons. If you're more interested in this question, how do they finally come up with this idea that smoking does cause lung cancer? You can take a look at your textbook. I think it's page 117. There's more information on smoking. They use genetics and twin studies to rule out this idea of it being a third variable, or that genetics was a confounding variable. It's very interesting. Take a look at that. Here's another example for generalization. I'm going to come back up to here and give you one more example here. Imagine using GCC students to predict average commute time for all community college students in Massachusetts or the USA. So your sample would be the GCC students, and your population would be all community college students in Massachusetts. Keep in mind that the GCC students may not be representative, or may not be a representative sample of all community college students, especially in regards to commute time, to live in a more rural area. So students are more than likely coming from greater distances and might have longer times or longer commute times. You could also argue the other way around. People in more urban areas have longer commute times because of the traffic, in which case GCC students are still not representative of all community college students in Massachusetts.